Today we are continuing to look at rate laws. This video will show you how to find rate law from an experiment or from experimental data. So this will help you with your next lab. The way we're finding a rate law is from experiments, and the method is called the method of initial rates. So when you do your lab, you look at the first part of the rate, not the rate for the whole reaction, because as the reactants get used up, then of course the collisions will decrease and the rate will decrease. So for example, calculate the rate law for BrO3 minus plus 5 Br minus plus 6H plus forms 3Br2 plus 3H2O. This is an example from your book, and here's the data. So you do several experiments. You do experiments such that there are experiments where each reactant is staying the same concentration and other experiments where they are changing. So for example, in experiment 1 and 4, bromate is staying the same and bromide is staying the same, but H plus is changing. So from experiments 1 and 4, we're going to be able to figure out how H plus affects the rate, because that's the only thing that's changing. So we can write the general rate law. This is called, well, it's almost the general rate law. This is the form of the general rate law. And then if we had X, Y, and Z, the reactant orders, that would be the general rate law. So it's always rate equals K times concentration of each reactant raised to some reactant order. And you have to figure out the reactant orders from the experiment. You cannot figure out the reactant orders from the overall balanced equation. So let's look at experiments 1 and 2. In experiments 1 and 2, bromide and H plus are constant and bromate is changing. So we can look at it just qualitatively now, kind of, well, it's numerically, but like, is it what's doubling, what's quadrupling, what's going down by a factor of half, that kind of thinking instead of math equations first. So we can see that bromate then is doubling. And so then we look at the rate. This would be 16 times 10 to the negative fourth and 8 times 10 to the negative fourth. So that means it's doubling the rate. So when concentration of bromate doubles, the rate doubles also. That means that the reactant order is 1. So then let's look at 2 and 3. So we can see in 2 and 3, bromate is constant, H plus is constant, and bromide is doubling. So that'll give us Y. So when bromide doubles, then the rate is also doubling, 1.6 times 10 to the negative third to 3.2 times 10 to the negative third. So that means that the reactant order for bromide is also 1. And finally, we can look at experiments 1 and 4. So H plus concentration is doubling, and the rate is going from 8 times 10 to the negative fourth to 32 times 10 to the negative fourth, so that's quadrupling. So since 2 squared is 4, that means that if if H plus doubles and rate quadruples, that the reactant order is 2. Okay, we can do the same example, but show how you would do it with math if you can't easily see what the relationship is between the concentrations and the rate. So what you do is you just write down the rate law with the variables for the reactant orders, and then you write down another rate law with variables for reaction orders, and you do the 2 experiments for the reaction order that you're trying to find. So if we do rate 4 and rate 1, we'll find z, and we just write them both and divide them. And then you plug in everything. So k is the rate constant, so for an experiment it's going to be constant, so that cancels out. Bromate for experiments 1 and 4 is the same concentrations, and it'll be the same reactant order, of course, and same with bromide. So all we're left with is H plus the Z power. So when we plug in our numbers for that, we have our rates, and then we have our concentrations to the Z power. So when we divide, then we get 4 equals 0.2 over 0.1, which is 2 to the Z power. And so then if you couldn't see what it was, then you could do something like take a natural log or a log of both sides. So then there's a rule for logs that says that when you have something like this, then the exponent can come out in front. So it turns into that. So then you divide both sides by a natural log of 2, and you solve for z, and you find out it's 2. So now we have all the reactant orders. So we have the general rate law. To get the complete rate law, to get the rate law, we need to also calculate k. So in experiment, a rule experiment, you'll probably get slightly different values of k for each trial that you do. So you'll want to calculate all of them and take an average. In book problems like this, they've probably set up the data so that all of them will turn out the same. So especially on an AP test or something like that, you just pick a trial. So we'll do trial 1. So you take the general rate law you calculated before, and you just plug in all the concentrations in the rate, and then you solve for k. And the tricky thing is units. People just forget the units, and so then on tests they lose some points. So make sure that your rate constant has units. The units will be different for every reaction that has a different sum of reactant orders. So to solve for a k, we're going to divide both sides by everything over here. So when I do it, I'm going to keep the units so that I can see how it turns out. So the number is 8.0. The units are going to be molarity per second divided by molarity to the 4th power. So molarity divided by molarity 4th is like molarity to the 1st power minus the 4th power, so that's going to be molarity minus 3rd power, and then seconds on the bottom. So that's going to be turned into those units. So when you do your lab, make sure you have enough experiments so that one reactant is not changing concentration while the other one is. Make sure the change in concentration is enough so you'll be able to see a good change in rate if the rate depends on that reactant. And then, since it's a method of initial rates, only measure rate for the first few seconds of your experiment, however long you need to get a good measurement for, not for until it stops, because it slows down and you won't have a good rate. And then if you read the book, you'll also see they talk about how if you start with one reactant a lot bigger in concentration than the other one, then that's another way to make sure that any change in rate is from the smaller one, basically, because the bigger one won't change very much over time compared to how much it starts with. Finally, for today, we'll look at what graphs of concentration rate look like. It's probably pretty obvious. We're just looking at the exponents, basically. So if we have a reaction where A is the reactant, let's make graphs if it turns out to be zero order, where the rate doesn't depend on the reactants, that'd be like rate equals K times the concentration of A to the 0 power. So no matter what concentration of A is, the rate stays the same. That happens usually if there's a catalyst. If it's first order, like rate equals K to the concentration of A first power, or second order, where concentration of A would be raised to the second power. So 0 order would be flat, since the rate does not depend on concentration. First order would be linear, and second order would be increasing rate, increasing slope.